Hello, and welcome to this webinar entitled Design Space of Flyback Transformers. In this presentation, we're going to explore some of the elements that represent boundaries or limitations when designing flyback transformers and the space between them. Here are the topics we'll look at. A little bit of background on flyback transformers and how they work, energy storage concepts, the minimum and maximum energy curve, duty cycle, reflected voltages, plus mixed mode operation and tolerances. The term flyback comes from the days of the cathode ray tube, which was used in televisions and monitors. Those tubes had a narrow electron beam that would scan the front surface of the tube, which was coated with a light-emitting phosphorus. The beam would scan across the tube, modulated by the signal, and when it got to the end, it would have to snap back to the start position and start the next scan. The snap back to the start was called flyback, and this required a horizontal deflection voltage between 5 and 10 kV. Flyback transformers were used to produce this voltage. Here's an example from a typical patent. It's not the earliest, but this one gives an example of all the elements that you'd have in a high voltage flyback transformer. It has a primary winding here and two secondary coils here and here connected in series. This is quite common in high voltage where you're trying to reduce the winding self-capacitance. You have a U-shaped core here and you've got some gaps here that store the energy. The whole thing is encapsulated in this cup, and then you have some auxiliary windings here and here. Today, the flyback transformers are almost all universal wide input charging adapters because of their ability to do the opposite. Take a variable high voltage input and produce a low voltage output. There are many topologies of flyback converters, including discontinuous conduction mode, continuous conduction mode, boundary conduction mode, quasi-resonant conduction mode, even things like force frequency resonant and mixed mode, where one control method is used over a portion of this voltage range and another is used for a different portion. The basic operation of a flyback is the same for all topologies. In the first period, when the switch is on, the current ramps up through the primary winding, building up a magnetic field. There's no current flowing in the secondary winding, and the load is supplied entirely from the capacitor. In the second portion of the cycle, when the switch is off, the collapsing magnetic field reverses the voltages. This allows the diode on the secondary to conduct, supplying current to the capacitor and load. There's no current flowing in the primary winding. Depending on the topology, there may be a dead time before the switch turns on, again, as in discontinuous conduction mode, or it may turn on immediately as in continuous conduction mode. The main points are that only one winding carries current at a time, and that the energy is transferred through the stored energy in the magnetic field. One winding is used to build up the magnetic field, the second winding is used to harvest the energy afterwards. This is unlike a transformer, where the energy is transferred instantaneously from one winding to another, with no delay. Here are the common control methods for flyback transformers. In discontinuous conduction mode, the current always returns to zero before the cycle begins again. The dead time is variable, while the frequency is fixed. In quasi-resonant mode, the currents again return to zero, but there is only a small dead time based on the resonance of the parasitics. The idea is to reduce switching losses. This is also known as valley switching. As a result, the frequency is variable, changing with input voltage or load. In the boundary mode operation, the current again returns to zero as before, but this time there's actually no dead time, so the next cycle begins immediately. This is sometimes called transition mode. Again, this will make frequency variable. Continuous conduction mode is where current is always flowing in the inductor. It never returns to zero. The first half of the cycle begins before the secondary fully discharges. Now, the frequency is fixed and the duty cycle varies only with the input voltage. The flyback transformer is very common in wide input, low wattage power supplies requiring less than 150 watts. The output power is limited only because the peak currents become very high. The advantage for this type of application is that the turns ratio can improve the duty cycle usage because the output voltage is not strictly fixed to the turns ratio as it would be in a real transformer. Also, with separate windings, galvanic isolation is provided to meet safety standard requirements. Plus, the flyback transformer has one of the lowest component counts of all switch mode power supplies, making it very effective. When looking at application notes on how to design a flyback transformer, most of them will only give you one formula for determining a single inductance value. In reality, there is a range or zone of values that could be used. This zone is bounded by different circuit elements. Things like minimum energy requirements, the switch's voltage ratings, applied component margins, or the ratings for reliability, operating frequency, and duty cycle limits, and finally, the PWM control modes. There are a few things that we need to understand before we start looking at the limitations. For efficiency, we want to use the converter's efficiency because the transformer has to be able to make up for the losses of other devices. Things like voltage drops and the output diodes can have a big impact unless we're using synchronous rectifiers. A well-designed transformer will have very low losses. Granted, the burden is switched back to transformers with the efficiencies of gallium nitride and silicon carbide, but these are not mainstream yet. Diode drops and the like have to be made up in the power that's transferred to the secondary side. Also, somewhere we have to set a boundary between constant conduction mode and discontinuous conduction mode. This is usually around 50% duty cycle. The control response changes quite a bit when crossing over this boundary, so it's important to set it. There are a couple of ways to look at the problem. One is to see it as a DC transfer function, and the other is to use the load resistance as the basis for calculations. Either will work. Lastly, in continuous conduction mode, the duty cycle does not change with the load. The duty cycle only changes with input voltage, so it's basically a constant voltage converter. Whereas in discontinuous conduction mode, the duty cycle changes with the load and with the input voltage because it's basically a constant current converter. Let's look at some of the limitations. Leakage inductance comes from less than perfect coupling between the windings, and this stored energy has to be dissipated when we turn off the switch. This is usually done with some type of snubber to dissipate that energy and also to limit the voltage spikes that result. The secondary side voltage is going to be reflected to the primary, so that voltage gets added to the input voltage and has to be provided for in the switch voltage rating. If you're going from a high voltage to a low voltage, that reflected voltage is going to increase as it goes back across to the primary side. MOSFETs have a fixed drain source voltage, and it usually has to be derated so that it's a limitation as to how much reflected voltage we can have. Similarly, on the secondary side, there are diodes with voltage limits, and the primary voltage is going to be reflected across to those voltages. Even though the IC duty cycle might work from 0 to 100, the converter won't be able to use the full range. The rated currents of the switch and the rectifier may be a limitation, especially for ICs with built-in switches. Here's a nice graphic from an ST Micro application note that illustrates all the voltages I've been talking about. The MOSFET has a limit to the voltage that can be presented across it in the off state, and that usually has to be derated or margined to provide for long-term reliability. We have three other voltages to account for: the maximum input voltage, the reflected output voltage, and some allowance for the leakage inductance spike. These three must add up to be less than the margined MOSFET voltage. Assuming the MOSFET voltage is fixed, the two things you can adjust are the turns ratio, which will adjust the reflected voltage, and to a lesser degree, the leakage inductance. You have the option of a voltage clamp or snubber that can also provide some control here as well. You also have to think about what are the worst case operating conditions. In a discontinuous conduction mode, The worst case condition will be under the highest load with the lowest input voltage, which will push the duty cycle to its maximum. That is one corner of the design. And at the other end is the condition of no load or minimum load with maximum input voltage, which should result in minimum duty cycle. Another thing that has to be taken into account is short circuit current protection limits. There are tolerances and temperature coefficients on all these components. Even simple things like small capacitors added for noise filtering can cause delays in response. The core material itself also has a temperature characteristic to consider. Just as ice cream comes in many flavors, inductance also comes in many different forms. We throw around the word inductance pretty loosely, but there are actually many specific types that we often call inductance, using them interchangeably, assuming the user knows what we mean. For the most part, it doesn't hurt us, but let's take a moment to look at the more prevalent versions of inductance that we use when we're designing transformers and inductors. These definitions come from the matching flavors of permeability. Usually, when we talk about inductance, we're talking about chord inductance, also known as amplitude inductance. That's the green line that starts at the origin and goes up to some point on the BH curve. It's the slope of the straight line, the chord along the curve. The slope is steepest with low magnetization force or current and decreases as it moves into saturation. Differential inductance is a slope that is tangent to the BH curve at some point where there is a small amount of change in magnetizing current and flux from a signal. The reversible inductance is very similar. This is what we see in a choker inductor that has DC bias, putting the AC ripple operating point somewhere along the curve. You can see that this minor loop would have a lower inductance than if it was measured as chord inductance. Neglecting losses, differential and reversible inductance are the same. Energetic inductance is the stored energy in the shaded areas. Normally, differential inductance is less than energetic inductance, which is less than the chord inductance. In a discontinuous mode, flyback is like on the left with chord inductance. Much more energy storage is available compared to the right side, which is like a continuous mode flyback. What is the energy capacity of the core? We need to know this to do a design. From the basic energy equation, you can show that the energy capacity of a core is dependent on three parameters. First is the maximum usable flux. This depends on the topology, as we saw in the last slide, and also on the core material. Second, the cross-sectional core area, which varies with the overall size of the core's volume. The magnetic flux level of the material is going to influence the size. Lastly, the AL value, which is really a proxy for the gap. AL varies with gap length. We have to understand that the energy capacity of the core is related to the volume size of the gap. If you want more energy in the core, you have to make it bigger, because there's a saturation limit to the core and there's a limit to the gap size before fringing becomes too large. Therefore, the only thing you can do is increase the cross-sectional area. The energy capacity of an inductor is 1/2 Li squared. The energy capacity of a core is equal to the core area times the magnetic path length times B squared divided by 2 mu naught, which is 4 pi times 10 to the minus 7th, and the effective permeability. You can condense some of these terms to AL, resulting in this formula. This tells us that increasing the flux helps by the square property, increasing the core area does the same, and increasing your gap, which reduces AL, are the only options. Here's a chart that illustrates the idea using an RM8 core as an example. This fixes the cross-sectional core area. Across the horizontal axis, we have increasing flux density, and the vertical axis is energy. Each of these lines represents a different AL. A larger gap has a smaller AL. You can see the exponential component in the curvature of the lines. As the gap increases and as the flux density increases, there's a large increase in the energy capacity of the core. This chart is often found in data books, and it's showing you the same thing. Each of these lines represent an AL value, or in this case it's labeled effective permeability, which is a proxy for AL value. A larger gap results in a smaller effective permeability, and it handles more magnetizing force before it falls off and saturates. The drop-off in the curve represents saturation, where the inductance would drop off. You can think of these as BH curves on their side. These two charts show you the effective temperature on core material and how it can be drastically different. These are from two inductors, one made from ferrite and one made from powdered iron. Each of the lines represents a different temperature, the blue line being the coldest at -60 Celsius, working its way up to 140 Celsius with the red line. You can clearly see that the saturation point of the ferrite, where it loses its permeability. The drop-off starts earlier at lower currents as the temperature increases. This is very important for a wide temperature range application, that the design stay within the limits of the core. You don't see the same effect on the powdered core. All 6 lines are pretty much on top of each other, indicating there is no change in the saturation level with increasing temperature. You should also realize that on the right, this is only a 6 microhenry inductor, whereas on the left, it's a 300 microhenry inductor, which would have a much smaller gap and be more sensitive to changes in material. The larger the gap in ferrite, the less sensitive it would be to variation. There's a couple of ways to look at some of the inevitable trade-offs. We can look at it from an inductance versus duty cycle point of view, or from an inductance versus reflected voltage or turns ratio point of view. At some point, we have to start pinning this down. In either case, you need a minimum amount of energy during each cycle. This comes from the energy equation, where energy equals 1/2 Li squared. We also know that L times di equals V times dt, and that dt equals duty cycle over frequency. Putting all this together, collecting our terms, gives us energy equal to V squared times duty cycle squared times frequency squared divided by 2 times the inductance. Here's an important point to grasp. Inductance versus duty cycle versus size. As the maximum duty cycle increases, the inductance needed decreases while the peak current increases. We know that energy storage is proportional to inductance times peak current squared, while the inductor size is proportional only to inductance times peak current. Recall that EDT equals LDI. If we double I peak, it will reduce the inductor to 1/4, and that will reduce the required core size in half. Looking at this chart for a duty cycle of 0.5 and the normalized current is 0.2 with a normalized inductance of 0.4. If we double the current to 0.4, the inductance is decreased by 1/4 to 0.1. The object is to make the duty cycle as large as possible for the smallest inductor. Let's start by putting everything together to map out the boundaries. We know the minimum energy is going to depend on the inductance and the peak current, but we may not always know exactly what the peak current is beforehand, or it might be flexible. I also have to know the total power out, which comes from the specifications. I must estimate an efficiency, and we need to know the minimum operating frequency. Combined together, these give us a minimum inductance according to this formula. I'm going to plot this on a chart where the vertical axis will be the inductance, and then across the bottom I'm going to plot duty cycle, though it could be any number of things like reflected voltage. The L minimum line represents the minimum inductance without any allowance for tolerance and is our bottom fence. The next thing we want to do is plot the critical inductance. This is going to be where the dead time goes to 0. It's the boundary inductance separating discontinuous conduction mode and continuous conduction mode. If we were going for boundary mode, the inductance here would be just right, just like in the Goldilocks story. This is going to be affected by the turns ratio, which we may not have finalized, yet initially we can use the voltages to help get us there. Adding the critical inductance plot to our chart is going to give us another straight line. We now have two of the boundaries, with the duty cycle being variable. We can't have an inductance any higher than the critical inductance if we want to stay in discontinuous conduction mode, and we have a minimum inductance to transfer enough power. We now have two sides of our box, and we can go on to calculate the sides. As mentioned earlier, one of the things we have to account for in the design is leakage inductance and the self-winding capacitance. We haven't even decided what type of core we're going to use or how many turns will be on it. All of this information we will have after we have gone through the design and built the actual transformer, but for now we have to use reasonable estimates because these do play an important role, especially leakage inductance, which is going to produce a voltage spike, and that's a function of the peak currents, the winding self-capacitance, and the MOSFET's capacitance. The only values we might have are the MOSFETs. For the rest of them, we're going to have to pick values that are typical as a starting point to get going. As discussed, there's a limitation to the turns ratio range. The maximum input voltage, the reflected secondary voltage, and the primary side switching MOSFETs, VDS, we talked about earlier, are all going to limit how high the turns ratio can be. It's also going to be limited by the reflected primary voltage and the secondary side's diode rating. If these are all fixed, it's a limitation. If they're free to be chosen, we'll have more space. We're also limited by the maximum duty cycle that we can support either by our control system or by our topology, and the minimum input voltage. Here are three formulas. From the two different formulas for minimum turns ratio, we will use whichever is greater. Included in the values are our assumptions and any deratings required by design guidelines for reliability. Two different curves are the result. On this chart, we've plotted both of these curves for Vin max and Vin min based on the turns ratio and the B max that we've chosen. Now we actually have a box which bounds our choices on all sides, top and bottom by minimum and maximum inductance, and left and right by input voltage and turns ratio. We can pick any inductance inside this box and it will work. Now you'll notice that I've labeled each of these lines with a suffix LF. The reason I've done this is in the next slide. In this slide, I've reproduced the same calculations, but I've used a higher frequency so you can see the effect of frequency tolerance. It could be as simple as the tolerance of the IC's fixed frequency, which might be 5%, or it could be a function of the external components that you use to set your frequency, or it could be your operating range for a variable frequency topology. It results in a smaller range that narrows your box, and it can narrow considerably if there's a big range. Previously, between the blue lines, we had a large area to work with, and if we're working at the higher frequency, we would have a smaller area bounded by the purple lines. We can actually only use the area that's overlapping, so now you have a very small zone. Your operating duty cycle and inductance is going to have to fall into this range. By putting these different fences on the four sides, you've narrowed down your box to where you know the parameter is needed for the transformer to work under all the conditions that we stipulated in the beginning. Now that we know what our possible inductance ranges is, we have to select a core. In Flyback, the primary inductance is that of a storage inductor, but the primary transformer needs additional space for the output inductor winding, which we call the secondary, and also for insulation. Rather than being a single inductor, which would be the smallest possible size, it's actually two windings on one core, so it has to be bigger. If we want lower losses, it's probably going to be a little bigger, because we want to run a lower flux and/or it's going to use a lower loss core, which might be more expensive. If it's an offline converter, we have to allow space for creepage and clearance distances, which will add to the overall size. In the end, there's no direct way to the optimal transformer. There are a large number of partially contradictory requirements that have to be met simultaneously. We've seen that there are many parameters that depend on each other, and we don't always know exactly what those parameters are at the beginning. This is why transformer design is reiterative. We have to make some initial guesstimates, plug them in, do our calculations, refine those calculations, and then build a part to verify it, and maybe go back again. The designer has to make many decisions along the way, and often based on their experience. It's a truism that the more designs you do, the better you get at designing. This is an interesting set of formula and a graphic from Hurley and Wolf's book about how to pick the optimal effective permeability for an inductor, which is another way of saying what's the optimal gap. On the left side, we have energy in terms of copper losses, and on the right side, we have energy in terms of flux density. The idea is to maximize both of these at the same time, which they illustrate in this diagram. Along the horizontal axis on the left side are power losses, which change linearly, and on the right side is BSAT, which changes exponentially with energy, which is the vertical axis. You can think of the colored lines as fixed, but they can rotate together about the origin. If you look at the chart at the brown line, you can see that it's touching the BSAT, so you're using the maximum amount of flux available, but you're not using the maximum amount of power dissipation, so this has low energy. On the blue line, you can see that you're using the maximum amount of power dissipation, but you're not using the full amount of flux density. So again, you're not getting the maximum energy out of the core that you possibly could get. And of course, the green line, you're using the maximum power dissipation, and you're using the maximum amount of flux available. So you have the optimal amount of energy for your design, which should result in the smallest core. So just a note about tolerances. Every component in the circuit has a tolerance. Obviously, some of those are going to be more critical than others. Some of them are going to compensate for each other, so the point is you don't want to overstack them and make something that's very large. Here are some of the considerations for discontinuous conduction mode. You can have too much inductance, and this may cause your converter to go into CCM mode, which will upset your control. You may not even have enough power output. Though it seems counterintuitive, to get more power out of a discontinuous mode transformer, you're probably going to have to lower the inductance. Remember, the energy is 1/2 Li squared. As you decrease inductance linearly, current will increase exponentially. If you had infinite inductance, you'd have no current, and then you'd have no power transfer. Inductor tolerances are variable. They can be plus or minus 10%, usually for transformers. Straight inductors typically have wider tolerances, so you have to be careful to make sure that you specify what you need. The controller is going to have tolerances for things like frequency, duty cycle, and current limits. It's always a good idea to have a bit of play in the duty cycle, so you don't want to run up to 50% if that's your max. You'll want to operate a few percentage below so that the converter can respond well to transients. Same with your current limit. Lots of current limit circuits have little noise filter capacitors in them that delay the response time, which could be critical to understand under worst case conditions like a short circuit. You don't want to be saturating the core. So let's summarize. There are many factors that must be considered when designing magnetics. Many are unknown initially and must be estimated. They often interact with each other, and they are often contradictory, which means to improve one element means letting the other element get worse. Leakage inductance versus winding self-capacitance is a classic. These can be viewed as limitations or opportunities. The scope of possibilities is very large at the beginning, but narrows very quickly once choices are made. It's true that the more design you do, the better you will be at design. This concludes our short presentation, Design Space for Flyback Transformers. Thank you for watching.